So, what is econometrics? Well, it's the use of statistical methods to analyze economic data, and this enables us to study economic relationships. For example, the impact of education on income or interest rates on consumer spending. Econometrics has three major uses: describing economic reality, testing hypotheses about economic theory and policy, and forecasting future economic activity. Now, regression analysis attempts to explain movements in one variable, the dependent variable, as a function of movements in a set of other variables, the independent or explanatory variables. So there's a linear relationship. For example, y equals to b0 plus b1 multiplied by x, where y is the dependent variable, b0 is the y-intercept, b1 being the gradient or the slope, which is the amount y changes by if there's a 1-unit change in x, and then x being the independent variable. Now, a regression result can prove causality. All it can do is test whether a significant quantitative relationship exists. b1, the gradient or the slope, is equal to the change in y divided by the change in x. So y2 minus y1 divided by x2 minus x1. Now let's talk about the stochastic error term. Well, this is a term that's added to a regression equation to introduce all the variation in y that can't be explained by the included x's. So we can't possibly include every variable that influences the outcome. This could be from omitted variables, incorrect functional forms, measurement error, or purely random occurrences. And so the equation becomes y is equal to b0 plus b1x plus u or e, which is the error term, or the disturbance or randomness. Now this equation has two components, the deterministic component and the stochastic component. The deterministic component is y is equal to b0 plus b1x, which is also called the expected value of y given x. So y given x is equal to b0 plus b1x. And then we have the stochastic component, which is u or e, or it could be y given x is equal to b0 plus b1x plus u or e. Now we can't observe the values of the true regression coefficients, so we calculate estimates of those coefficients from the data. And so the regression estimate is y hat is equal to b0 hat plus b1 hat multiplied by x plus e. Now let's talk a bit about ordinary least squares. Now here we essentially try to minimize the error between our observed values of y and the estimated values of y, so the y hat, from the sample or data. And so the normal y is the observed y from the sample or data, and then y hat is equal to b0 hat plus b1 hat multiplied by x, which is the estimated regression. And now the difference between the actual value of the dependent variable and the estimated value of the dependent variable is the residual, e. E is equal to y minus y hat. So what happened versus what our model predicted? Now let's take a look at some of the differences between the residual, ei, versus the error term, ui. So the residual is the difference between the actual y and the predicted y. So the difference between y and y hat. It's observable, calculated from the sample, and it measures the model fit in the sample. And then the error term is the true unobserved error, assumed in the population model. It captures the randomness and omitted factors in real life. And so the residuals are observed sample-based estimates of the true stochastic error, which we can see. Now in terms of model types, we have a single variable model or regression, which consists of only one independent variable, and a stochastic error term or the residual. So y is equal to b0 plus b1x plus ei. And then we have a multivariate model or regression which consists of more than two independent variables and a stochastic error term. So y is equal to b0 plus b1x plus b2z plus ei. And so when they ask you to interpret the model, b0 tells us the mean value of y when x and z are both 0, so when the explanatory variables are 0. And then b1 or 2, the gradient or slope, tells us the increase in the mean value of y for a 1-unit change in x or z, holding the other value of x or z constant. And so in terms of the purpose of OLS, or ordinary least squares, it calculates b0 and b1 estimates by minimizing the sum of squared residuals, and thus minimizing bias. And so RSS, the residual sum of squares, is equal to the sum of e squared from I is equal to 1 to n. And so OLS is an estimator. It's a mathematical technique applied to a sample of data to produce an estimate of the true population regression coefficient. We use the squared variations of y around its mean as a measure of the amount of variation to be explained by the regression. This computed quantity is called the total sum of squares, TSS. And so TSS is equal to the square difference of y minus y bar from I is equal to 1 all the way to n. And for ordinary least squares, the TSS has two components: the variation that can be explained by the estimated regression, ESS, the explained sum of squares, and the variation that can't, RSS, which is the residual sum of squares. The explained sum of squares, ESS, is the amount of the square deviation of y from its mean that's explained by the regression line. And then the residual sum of squares, RSS, is the unexplained portion of TSS, unexplained by the estimated regression equation. And so TSS is equal to ESS plus RSS, which is thus equal to the square difference of y minus y bar from 1 to n, which is equal to the square difference of y hat minus y bar from 1 to n, plus the sum of e squared. And so we call this the decomposition of the variance. Now, how do we go about deriving the OLS minimization objective function? Well, you're usually given y is equal to b0 plus b1 multiplied by x plus ei. Now, the first thing we need to do is make e the subject, so e is equal to y minus b0 minus b1x. Then we find that the squared sum of y minus b0 minus b1x from 1 to n is equal to the RSS. And then we move on to showing the first order conditions for the coefficients excluding the constant using the chain rule. And so the first thing we need to do is get the derivative of RSS with respect to b0. And this is the squared sum of y minus b0 minus b1x from 1 to n, which is equal to 0. Then we get the derivative of RSS with respect to b1. And this is pretty much the same thing. It is the squared sum of y minus b0 minus b1x from 1 to n, which is also equal to 0. And then finally, we take partial derivatives of RSS with respect to each b parameter or slope parameter. So we get the derivative of RSS with respect to bj, and j could be any b. And then we find that this is equal to negative 2 multiplied by the sum of xji multiplied by y minus b0 minus b1x1 minus b2x2, etc., which finally is equal to 0. Now let's take a look at a measure of goodness of fit, r squared, or the correlation coefficient squared. So r squared is the ratio of the explained sum of squares to the total sum of squares. So r squared is equal to ESS divided by TSS, which is equal to the squared sum of y hat minus y bar from 1 to n divided by the squared sum of y minus y bar from 1 to n. And r squared is between 0 and 1. The higher the r squared, the closer the estimated regression equation fits the sample data. If r squared equals to 1, it's an excellent overall fit. If it's equal to 0, then it's poor or no fit, which means the estimated regression can't explain observed y values better than the sample mean, y bar. A major problem with r squared is that adding another independent variable to the equation or model can never decrease r squared. Because of this, they developed another measure of the quality of the fit. This is the adjusted r squared, or r bar squared. This is adjusted for degrees of freedom, df. It measures the percentage of the variation in y around its mean that's explained by the regression equation. And remember, the degrees of freedom is equal to n minus k minus 1. And so r bar squared will increase, decrease, or stay the same when a variable is added to the equation, although the degrees of freedom do decrease as variables are added to the equation. It's also important to note that r bar squared isn't the only measure of model quality. Just because r bar squared is high doesn't mean the model is good. Some parameters or variables might not make sense. Now let's take a look at the steps in applied regression analysis. Well, the first step is your literature review and the theoretical model. So here you explain the research question or relationship you're trying to investigate, and what the literature infers about the topic and proposed theoretical model. For example, we're trying to determine how advertising spend affects monthly sales. Literature indicates spending more money on marketing or advertising should have a positive effect on sales or increase sales. And then the second step is specifying your model, setting up the regression model and explaining the parameters. For example, sales is equal to b0 plus b1 multiplied by advertising plus ei. Then we explain the parameters. So sales is sales in thousands of rands per month. B1 is the increase or decrease in sales for every unit change in advertising, etc. E being the other factors that may increase monthly sales, for example, staff productivity. And then the third step is to hypothesize the expected signs of the coefficients. So here you explain the type of relationship you expect from all the coefficients, and it should reflect theory from step 1. For example, based on the theory, I'd expect that higher ad spend leads to higher monthly sales, so B1 should be positive. Now the fourth step is collecting and cleaning the data. So how is the data collected? Where was it obtained? And then cleaning the data, and how'd you go about it? For example, we collected monthly sales and ad spend data for 12 months. Then we clean the data by removing blanks, duplicates, inspecting outliers, and aggregating to monthly sales scales. And here you should know that the more observations, the better. The fifth step is estimating and evaluating the equation. So here you show the estimated model and interpret the coefficients and other statistics, and you explain the coefficients, B0 and B1, p-values, confidence intervals, r-squared and r-bar squared, and what the specific value means. For example, let's say the regression equation we get is y is equal to 45.3 plus 6.5 multiplied by advertising plus EI. R-bar squared is equal to 0.69 and the t-value is 4.45. So B0 is equal to 45.3, therefore monthly sales when ad spend is equal to 0 is equal to 45,300. B1 is equal to 6.5, which means that monthly sales increases by 650 Rand for every 1 Rand spent in advertising. R-bar squared is equal to 0.69, which means that 69% of the variation in monthly sales can be explained by the model, etc., etc. And then the sixth and final step is to document the results. So link your result with the expectations you had in step 3, list all the assumptions of the model, and talk about the procedures and data used. For example, the result shows a positive relationship between advertising spend and monthly sales since B1 is equal to 6.5. This aligns with the theory and hypothesis set out before, etc., etc. Now, in terms of an overview of the classical model, it states that for OLS estimates to be the best, so unbiased or efficient, a set of 7 key assumptions must be met. If one or more of these assumptions are violated, other estimation techniques may be superior to OLS. And so now let's take a look at these 7 classical assumptions. Well, the first assumption is that the regression model is linear, correctly specified, and has an additive error term. So the model must be linear in its parameters, for example, y is equal to b0 plus b1x1 plus b2x2, etc., etc. It should be correctly specified, meaning no omitted variables and the correct functional form is used, and the error term must be additive. It can't be multiplicative or divisive with the explanatory variables. And then the second assumption is that the error term has a zero population mean. So the expected value, the error term given x, is equal to 0. So in any given sample, the mean may not exactly be 0, but it should approach 0 as the sample size increases. Including a constant term, b0, in the equation absorbs any non-zero mean in the sample, preventing this violation from biasing the other coefficient estimates. And then the third assumption is that all explanatory variables are uncorrelated with the error term, so the covariance of the error term in x should be equal to 0. This assumption is commonly violated by omitting an important variable. The effect of the omitted variable gets absorbed into the error term, and if that variable is correlated with an included variable, OLS mistakenly attributes the omitted variable's impact to the included one, causing biased estimates. The fourth assumption is no serial correlation or autocorrelation. So error term observations must not be correlated with each other, so the covariance of error term I with error term j should equal to 0. Violation of this means that OLS estimates are less precise or inefficient, leading to incorrect standard errors. And this is a concern in time series data where a shock in one period shouldn't systematically affect the error term in another. The fifth assumption is that the error term has a constant variance, so no heteroskedasticity. So the variance of the error term given x should equal to the standard deviation squared. So variance of the error term must be constant across all observations, otherwise standard errors are inaccurate, undermining hypothesis tests and confidence intervals. The sixth assumption is that there's no perfect multicollinearity. So no explanatory variables can be a perfect linear function of any other explanatory variables. Perfect collinearity makes it impossible for OLS to distinguish their individual effects. And then the seventh and final assumption is that the error term is normally distributed. This assumption isn't required to calculate OLS estimates themselves, but it's critical for inference, conducting hypothesis tests, and making confidence intervals to determine statistical significance. Now let's talk a bit about the sampling distribution of B, or the slope parameter. So each sample from a population yields a different B estimate. The distribution of these estimates is called the sampling distribution. A good estimator is unbiased, meaning the average of its sampling distribution is equal to the true population parameter. So the expected value of B hat should be equal to B. The precision of the estimate is measured by its variance and its standard error. A larger sample size decreases the standard error, leading to more precise estimates. So on a graph you see the true B estimate and then a bunch of bell curves. you'll see two bell curves that are unbiased, but one with a small variance and one with a large variance, as well as one that's biased because it's far from the true B estimate, although it has a medium variance. Now, what is the central limit theorem, CLT? Well, it states that as the sample size increases, the sampling distribution of B becomes approximately normal, even if the underlying data isn't, and so the variance of the sample mean shrinks as the sample size grows. This justifies the use of normal or t distributions for hypothesis testing and confidence intervals with large samples, even with the messy real-world data. Now, what is the Gauss-Markov theorem? Well, it tells us why the classical assumptions are important. It states that under certain classical assumptions, excluding normality of errors, the OLS estimator is BLUE, B-L-U-E, the best minimum variance, linear, unbiased estimator. This means that among all linear and unbiased estimators, OLS provides the most precise estimates with the least variance. Now let's move on to hypothesis testing. Well, this process tests if a result is statistically significant or likely due to chance. And so the null hypothesis, H0, is the hypothesis of no effect, or the status quo that the researcher expects not to find. For example, HO would be that B1 is equal to 0. And then the alternative hypothesis, H1 or HA, is the hypothesis that the researcher expects to be true. For example, H1 would be B1 does not equal to 0, so it has an effect. And with hypothesis testing, we have two types of errors. Type 1 errors are when we reject a true null hypothesis, and type 2 errors are where we fail to reject a false null hypothesis. Then in the hypothesis test, we move on to the t-test, and this is used to test hypotheses about individual regression coefficients. For example, HO would be B1 is equal to 0. So first you'd calculate the t-statistic, or the calculated t-value, which is equal to the estimate of B1 minus B1 divided by the product of the standard error and the estimate of B1. Then we'd calculate the degrees of freedom, and that's equal to n minus 1 minus k, k being the number of explanatory variables in our regression model. Then we'd use our t-table to find the critical t-value by getting the coordinates of the degrees of freedom and alpha, which is usually 5%. And then finally, if the t-statistic or the calculated t is larger than the critical t-value, then we reject the null hypothesis, or HO. So effectively, the result is compared to the critical t-value from the t-distribution based on the chosen significance level, A being the maximum acceptable probability of a type 1 error, which is usually 5%. Now, in terms of p-values, this is the probability of obtaining a result at least as extreme as the one observed, assuming the null hypothesis is true. A small p-value, which is less than 0.05 for a 5% significance level, provides evidence against the null hypothesis. So you'd reject HO if the p-value is less than your chosen alpha. Then we have confidence intervals. This provides a range of values that likely contains the true population parameter. So the confidence interval would equal to the B estimate plus or minus the critical t-value multiplied by the standard error multiplied by the B estimate. If a hypothesis value like 0 falls outside of the confidence interval, you can reject the null hypothesis at that confidence level. And then within hypothesis testing, we also have the F-test, the test of overall significance. While the t-test checks coefficients individually, the F-test evaluates joint significance of multiple coefficients simultaneously. For example, testing if all slope coefficients in a model are 0. So the null hypothesis would be that B1 is equal to B2, which is equal to 0. So the model has no explanatory power. Whereas the alternative hypothesis is that at least one B does not equal to 0. And so a calculated F statistic larger than the critical value from the F distribution leads to a rejection of the null hypothesis, indicating that the model as a whole does have explanatory power. And so the calculated F statistic is equal to the ESS, the estimated sum of squares, divided by K, which is the number of constraints or parameters in the null hypothesis, divided by the RSS, the residual sum of squares, divided by n minus k minus 1. And so the coordinates of the critical value of the F statistic would be df1 and then df2, and then alpha would be equal to 0.05. And then if the calculated F statistic is larger than the critical F value, then we reject HO with the null hypothesis. Therefore, the overall model is significant. Now, specifying an econometric model consists of three parts. The first is choosing the correct independent variables. Second is getting the correct functional form. And third is getting the correct form for the stochastic error term. to avoid specification error. Now, what are emitted variables? Well, these are relevant and important explanatory variables that have been incorrectly left out of a regression equation. Emitting a variable z that's correlated with an included variable x violates the classical assumptions and causes bias in the estimated coefficients. And this bias isn't random. The expected value of the coefficient for x, b1 star, becomes the true value, b1, plus the product of the effect of the emitted variable, b2, and the relationships between the emitted variable and x, or a1. If z is emitted, the expected value of b1's coefficient is equal to b1 plus b2 multiplied by a hat 1, a1 being the estimate of the slope coefficient of a secondary regression that relates z to x. This means the estimated coefficient will systematically overstate or understate the true relationship. Now let's talk about choosing independent variables. So you'd usually select independent variables based on economic theory. Other statistical criteria can be used to support the decision. And just to recap, the t-test is to check the individual significance of a variable. Adjusted R-squared is to see if a new variable improves the model's explanatory power after accounting for the number of variables. And then bias is to assess if emitting a variable causes bias in other coefficients. We should still avoid specification searches like data mining that prioritize statistical fit over theoretical validity. And now, what is a specification search? Well, this is the process of selecting the correct functional form, variables, and transformations in a regression model, and is done to avoid bias and improve fit. For example, you're studying the effect of education on wages. So you start with wage equals to b0 plus b1 multiplied by edu plus the error term. Then you realize experience matters, so you add an experience variable to the model. Then you see there's nonlinearity in experience, so you add experience squared. And then you include a gender dummy variable to show wage differences. And so the final model would be wages is equal to b0 plus b1 multiplied by edu plus b2 multiplied by experience plus b3 multiplied by experience squared plus b4 multiplied by the gender dummy variable plus ei. Now, in terms of choosing the functional form, the best functional form is the one that best matches the underlying theory of the relationship. A linear form would mean that a 1 unit change in x changes y by b1 units. Double log form would mean that a 1% change in x causes a b1% change in y. So b1 is elasticity. And here we'd get the natural logarithm of both x and y. And then the semi-log form with respect to x would mean a 1% change in x changes y by b1 divided by 100 units. And then a semi-log form with respect to y would mean a 1 unit change in x changes y by approximately 100 b1%. And then in terms of the polynomial form, the change in y depends on the current level of x. And here we'd have x squared. Now, dummy variables are used to include qualitative, categorical concepts, for example, gender or regions, in a regression model. They take the values of 0 or 1 to indicate the absence or the presence of a category. The coefficient on a dummy variable represents the effect on the dependent variable of being in the given category, which should be coded as 1, relative to the emitted baseline category. Now, there's also a dummy variable trap. We need to avoid perfect multicollinearity. If a qualitative variable has m categories, only include m-1 dummy variables in the model. Now, let's take a look at slope dummy variables or interaction terms. An intercept dummy could, for example, be b2 multiplied by d, so the slope parameter multiplied by the dummy variable. So the intercept dummy changes the constant or intercept term depending on whether a qualitative condition is met. It causes a parallel shift in the regression line. And then the slope dummy is where the slope parameter is multiplied by the independent variable, which is also multiplied by the dummy variable. So this is an interaction term between a quantitative variable and a dummy variable, and it allows the slope of the relationship to differ for a specific group. The combined model could look something like y is equal to b0 plus b1x plus b2d plus b3x multiplied by d plus e. And this allows for both different intercepts and slopes between groups. Now let's talk about multicollinearity. So multicollinearity occurs when independent variables in a regression model are highly correlated. Perfect multicollinearity is where one independent variable is a perfect linear function of another. And this is a violation of a key classical assumption. This type is rare and usually avoidable with careful variable selection. And then we have imperfect multicollinearity. This is more common, where variables are strongly but not perfectly correlated. A special case is where we have a dominant variable, which is a variable that is definitionally related to the dependent variable. For example, including total revenue as an independent variable when explaining profit. It acts like perfect collinearity with the dependent variable, masking the effects of all other variables. But then what are the consequences of multicollinearity? Well, firstly, you have unbiased estimates. The OLS coefficient estimates, so the B's, remain unbiased. But we get increased variances and standard errors for estimates. It becomes hard to isolate the individual effect of each variable, leading to less precise estimates. Another consequence is lower t-values and wider confidence intervals. The increased standard errors cause t-scores to fall, making variables appear statistically insignificant. Confidence intervals for the coefficients also become wider. Another consequence is that the estimates become highly sensitive to model changes. Coefficient estimates can change dramatically when adding or dropping a variable or a few observations. And then the final consequence of multicollinearity is unaffected overall fit. The model's overall explanatory power, R squared, remains high or unaffected even when individual variables seem insignificant. Now let's move on to the detection of multicollinearity. So some multicollinearity exists in virtually every regression model. The goal of detection isn't to find out if it exists, but to determine how severe it is. The aim is to find variables that are both theoretically relevant and statistically non-multicollinear. So there are two primary methods for detection. The first is high simple correlation coefficients, R. This examines the pairwise correlation between two independent variables. A high absolute value of R indicates the two variables are highly correlated, signaling potential multicollinearity. The limitation of this method is that it's a sufficient but not necessary test. High multicollinearity can exist between more than two variables. For example, x1 is a linear combination of x1 and x3, even if all simple correlation coefficients are low. We can also use high variance inflation factors, VIFs. This is a more general and reliable measure that detects whether one explanatory variable can be explained by all other explanatory variables in the model. The calculation involves two steps. The first step is that for each independent variable, xi, run an auxiliary regression, where xi is the dependent variable, regressed on all other independent variables. So step 1 would be x1 is equal to a0 plus a1 multiplied by x2 plus v. And then the second step is to calculate the VIF for the coefficient xi or bi using the R squared from its auxiliary regression. So in the second step we get the VIF of bi, which is equal to 1 divided by 1 minus R squared I. And so a high variance inflation factor indicates that multicollinearity has significantly increased the variance and standard error of the estimated coefficient. And so a rule of thumb is that a variance inflation factor that is above 5 or above 10 suggests severe multicollinearity. The limitation here though is that, like the correlation coefficient, the VIF is also a sufficient but not necessary test for multicollinearity. We should also know a VIF which is equal to 1 means that there's no multicollinearity. But now let's take a look at the remedies for multicollinearity. Well, first, we could do nothing. This is often the best action for two reasons. One is when there's minimal impact. The presence of multicollinearity doesn't automatically invalidate a model. If the t-scores remain significant and the coefficients align with the theoretical expectations, the model may be acceptable as is. Another reason we could do nothing is to avoid specification bias. Removing a variable that belongs in the model, even if it's multicollinear, introduces a specification bias, which is a more serious error than multicollinearity. Another remedy for multicollinearity is dropping a redundant variable. This applies when two or more variables are measuring the same underlying concept, for example, different metrics for wealth. Only one is needed to represent the effect on the dependent variable. The decision on which variable to drop should be guided primarily by theory, not just statistical measures. Another remedy could be increasing the sample size. Collecting more data can help by providing more information, leading to more precise estimates. A larger sample size reduces the variance of the coefficient estimates, thereby diminishing the negative consequences of multicollinearity. Another remedy is factor analysis or principal component analysis, PCA. These are advanced techniques that transform the original correlated variables into a new set of uncorrelated variables called factors or principal components. These new variables are then used in the regression, eliminating multicollinearity. Another remedy could be combining variables into a single variable. For example, instead of having an X variable for size and one for the number of bedrooms, we could create a variable for size per bedroom. Now let's talk about serial correlation. Serial correlation occurs when the error terms in a time series regression model are correlated across time periods. Time series data tracks a single entity over multiple points in time, making it susceptible to this issue. The error term is often affected by events from previous time periods. And so in terms of the types of serial correlation, we have pure serial correlation, and this is violation of the error term assumption in a correctly specified model. And then we have impure serial correlation, which is caused by a specification error in the model, such as an omitted variable or an incorrect functional form. And so first order serial correlation is where the current error term is a function of the previous one. So ET, the current error term, is equal to P multiplied by ET minus 1 plus UT. P is rho, which is the first order autocorrelation coefficient, which is between -1 and 1. And its magnitude indicates the strength of the correlation, which can be positive or negative. But then what are the consequences of serial correlation? Well, first, there's no bias in coefficient estimates if pure. Pure serial correlation doesn't cause bias in the coefficient estimates, but if it's impure from a specification error, the estimates can be biased. Another consequence is that OLS becomes inefficient. OLS is no longer the best linear unbiased estimator, blue, so there's no minimum variance and it's less precise. Another consequence is biased standard errors and unreliable hypothesis testing. The OLS estimates of the standard error of B1 are biased, usually underestimated. This leads to inflated t-scores, making it more likely to incorrectly conclude that a variable is significant, so a type 1 error. Hypothesis testing then becomes unreliable. Now, how do we go about detecting serial correlation? Well, first we have the Durbin-Watson test, the DW test, and this is to determine if there's first order serial correlation in the error term by examining the residuals. So this is specifically to detect first order serial correlation. And so the key assumptions or when to use it is when the regression model includes an intercept term, when the serial correlation is first order in nature, and when the model doesn't include a lag-dependent variable as an independent variable. The DW statistic, D, ranges from 0 to 4, and the formula is D is equal to 2 multiplied by 1 minus P or rho. This is the estimated first order correlation coefficient. So if D is equal to 2, there's no autocorrelation. If D is less than 2, there's positive serial correlation, and if D is larger than 2, there's negative serial correlation. And then in terms of hypothesis testing for positive correlation, the null hypothesis is that rho is less than or equal to 0, and this means there's no positive serial correlation, and then the alternative hypothesis is that rho is larger than 0, therefore there's positive serial correlation. And so the test involves comparing the calculated d-stat to two critical values from the table, dl and du. And so the decision rule is that we reject HO if d is less than dl, therefore there's positive serial correlation. The test has a region of indecision or inconclusive region if the d-stat falls between dl and du. Then we move on to the Lagrange multiplier test, the LM test. This is to test for serial correlation by seeing if lagged residuals are significant in explaining the current residual. So this test is more general and flexible than the DW test. The advantage here is that it doesn't have the same limitations as the DW test. For example, it can be used for models with lag-dependent variables and can test for higher order correlation. And so the procedure for the LM test is that you get the residuals, so you run the original regression and save the residuals, so ET, then run an auxiliary regression, so you regress the current residuals, ET, on all the original independent variables and the lag residuals, so ET minus 1, and then you calculate the test statistic, so LM is equal to N multiplied by R squared. N being the number of observations and R squared being the coefficient of determination from the auxiliary regression. And then finally, you test the hypotheses. So the null hypothesis is that rho 1 or P1 is equal to 0, so the coefficient of the lag residuals is equal to 0, therefore no serial correlation. And then obviously the alternative hypothesis is that P1 does not equal to 0, therefore there is serial correlation. And then if the calculated LM is larger than chi squared, we reject HO, therefore there is serial correlation. But now let's take a look at the remedies for serial correlation. So first we could use the generalized least squares, GLS, and the feasible generalized least squares, FGLS. So GLS is the primary method for eliminating pure first-order serial correlation and restoring the efficiency, so minimum variance, of the estimators. GLS transforms an equation that violates the classical assumptions due to serial correlation into one that meets them. And so the process is the quasi-differencing transformation. So first you start with a model with serial correlation. So yt is equal to b0 plus b1x1 plus et, where et is equal to rho multiplied by et minus 1 plus ut. And then step 2 is to remove p multiplied by et minus 1. And this is done by lagging the original equation and multiplying it by rho. And so the equation becomes p multiplied by yt minus 1, which is equal to p multiplied by b0 plus p multiplied by b1x1 t minus 1 plus p multiplied by et minus 1. And then we subtract the transformed equation from the original equation, so yt minus p multiplied by yt minus 1. And then finally, the result is a new transformed equation, so it's y star t, which is equal to b0 star plus b1x1 star plus ut. And so the new error term ut is free of serial correlation. Now, since the true value of p is unknown, it must be estimated. Using an estimated p or rho makes the process FGLS and not just GLS. Another remedy for serial correlation is first difference transformation. If autocorrelation exists, so it assumes rho is equal to 1, the model is transformed by taking the first difference of all the variables. Another remedy is Newey-West standard errors. Instead of fixing the serial correlation to make OLS efficient, this method adjusts the OLS estimates of the standard error of B, so the standard errors of the OLS coefficients, to make them reliable for hypothesis testing, even in the presence of serial correlation and heteroskedasticity. So it doesn't change the OLS estimates or coefficients, so the B's. Since pure serial correlation doesn't cause bias, the coefficients aren't changed. It does, however, change and produce standard errors, SEBs, that account for the correlation. Now we move on to some key concepts in time series analysis. Working with time series data introduces challenges because the order of the observations matter, unlike in cross-sectional data. So a distributed lag model could, for example, be yt is equal to b0 plus b1x plus b2xt minus 1 plus b3xt minus 2 plus et. These models explain the current value of a dependent variable y as a function of current and past values of x, so the independent variables. Now let's talk about stationarity. So a time series is stationary if its basic statistical properties, like its mean and variance, don't change over time. A series is non-stationary if one or more of its properties change over time. A common example is that the variance increases with time, which is also a form of heteroskedasticity. And so the consequence of non-stationarity is spurious regression. If two non-stationary variables are regressed on each other, they can appear to be highly correlated for non-causal reasons. This leads to misleading regression results. Inflated R-squared values or correlation coefficients and inflated t-scores can cause incorrect model specification by suggesting a significant relationship where none truly exists. To avoid this, it's crucial to ensure that time series variables are stationary before running regressions to avoid spurious results. Granger causality is a test used to investigate the direction of influence between two related variables when the causal direction is unclear. For example, does an increase in the money supply cause GDP to rise or vice versa? Now we move on to heteroskedasticity. Now, this is violation of the classical assumption that the error term in a regression model has a constant variance. It's the opposite of homoskedasticity, where the variance of the error term is the same for all observations. In terms of the types, we have pure heteroskedasticity, which is caused by the error term of a correctly specified model, and then impure heteroskedasticity, which is caused by a model specification error, such as an omitted variable. So heteroskedasticity often occurs in datasets with a wide range in the values of the dependent variable. Intuitively, the error term for large observations might have a large variance, while the error term for small observations might have a small variance. A common model shows the variance of the error term as being proportional to an exogenous variable, z. And so the variance of EI is equal to the standard deviation squared multiplied by Zi. Zi is the proportionality factor, and it causes the variance of the error term to change proportionally with it. This variable Z may or may not be one of the independent variables x in the regression model. Now, what are the consequences of heteroskedasticity? Well, you get unbiased but inefficient estimates. Pure heteroskedasticity doesn't cause bias in the OLS coefficient estimates, B. They remain unbiased and consistent, but OLS is no longer blue. Another consequence is biased standard errors. the standard errors of the coefficients, the standard errors of B, become biased. Heteroskedasticity also leads to unreliable and invalid hypothesis testing and confidence intervals. Now, how do we go about detecting heteroskedasticity? Well, before formal tests, preliminary checks are recommended. Checking for specification errors, for example, omitted variables, looking for early warning signs, for example, a dependent variable with a max value many times larger than its minimum value, and graphing the residuals against the potential proportionality factor Z, or the dependent variable, to look for patterns. Then we look at the formal test for heteroskedasticity. First, we have the Bruce-Pagan test. So the first step here is to obtain the residuals from the original regression, regress the squared residuals on the original independent variables in an auxiliary regression, and then test the overall significance of this auxiliary regression, for example with the chi-square test. H0 would be homoskedasticity, so A1 is equal to A2 which is equal to 0, and then H1 would be heteroskedasticity, so at least one A does not equal to 0. And if the p-value is less than 0.05, we reject HO. Then we have the Y test. So the first step here is to regress the squared residuals on the original regressors, their squared terms, and their cross products. And then the test statistic is n multiplied by r squared, or Lm, from this regression, which follows the chi-square distribution. This test is more general and flexible than the BP test. And again, HO is homoskedasticity, and if the p-value is less than 0.05, we reject HO. But then what are the remedies for heteroskedasticity? Well, first we could use weighted least squares, WLS. This is a direct remedy if the proportionality factor Z is known. The entire equation is divided by Z, and the transformed equation is estimated using OLS, resulting in a homoskedastic error term. It can be risky if the form of the heteroskedasticity is misspecified. Another remedy is redefining the variables, taking the natural log of the dependent variable y, or you could switch from a linear to double log functional form, which can reduce the variation and often eliminate heteroskedasticity. Finally, you could also use heteroskedasticity consistent standard errors, or white robust standard errors. This method doesn't change the OLS coefficient estimates, B, but corrects the standard errors, SCB, to make them consistent in the presence of heteroskedasticity. It allows each observation to have a different variance, but we should take caution that this technique works best in large samples and may be unreliable in small samples.